This is chapter 14 of the Klein text. We're looking at ethers and epoxides, and we'll also look at thiols and sulfides. I'm going to break this chapter up into different video segments, just so that you're not sitting for an hour listening to a video. An ether is a compound that has an oxygen bonded to two R groups. So you can see that here. Okay, here's your oxygen, and then here are your two R groups. Now the R groups do not have to be the same. And as you can see here from this figure from your book, ethers are a common functional group in natural products. So here we have melatonin, which is a hormone that's believed to regulate the sleep cycle, and here's your ether. Morphine, which is used to treat severe pain, and there's your ether. And vitamin E, which is an antioxidant, also contains an ether. And now we're in section 14.2, which is nomenclature of ethers. You need to review your nomenclature notes from Organic 1. Okay. For ethers, there are two ways that we can name an ether according to IUPAC rules. The first way is that you have a common name that is formed by identifying each R group and arranging them in alphabetical order, and then adding the word ether. So if you look at the two examples above, we have the ethyl group and the methyl group. So the name would be ethyl methyl ether. Here we have a methyl group and a terse butyl group, and you're going to alphabetize according to the butyl. So we have terse butyl methyl ether. The two previous examples were examples of unsymmetric ethers. Where there were two different R groups. When you have a symmetric ether, such as this ether here, and we have two ethyl groups. When we use the first way of naming ethers, this ether is a dialkyl ether. Okay? So we would name it diethyl ether because we have two ethyl groups. If we were to use the systematic way in IUPAC, we could generate a systematic name where we would choose the larger group as the parent, and then the smaller group would be the alkoxy substituent. For example, if you see here, we have an ethyl, so it would be ethoxy, and we have a pentane. So the systematic name would be ethoxypentane. We use systematic names for ethers that exhibit multiple substituents and chiral centers. So the idea is if you have a simple ether, you can use the common way, the common nomenclature, but if you have a more complicated ether, you use the systematic nomenclature. So let's look at some examples for nomenclature. Okay, so for the first one, we have a methyl substituent, then we have a butyl substituent. So we can name this as butyl methyl ether. Or we could name this 1-methoxy butane. For the second one, we have a methyl group and a sec-butyl group. So we can use the common way and call this sec-butyl methyl ether. Or if we use the systematic way, we would call this 2-methoxy butane. It would be 2-methoxy butane because here we have a butane, 1, 2, 3, 4, and I'll pick a different color to highlight to show you. This would be the methoxy substituent. With the next example, we have a methyl group again, and here we have an isobutyl group, so we could name this isobutyl methyl ether, or we could say that we have a methoxy substituent, and here we have a propane chain, 1, 2, 3, where the name would be the systematic name would be 1-methoxy 2-methyl propane. Alright, finally we come to the last example. And here we have an ethyl and an isopropyl. So this can be commonly called ethyl isopropyl ether, or we can say this is an ethoxy group and this is propane, and so the name would be 2-ethoxy propane. Okay, so these are examples of this common, so the first names are the common names. And then the systematic names. Both are accepted in IUPAC nomenclature. Okay, now we come to section 14.3, where we're looking at the structure and properties of ether. If you look at the oxygen atom, it is sp3 hybridized. The orbitals are arranged in a nearly tetrahedral shape. And you can see the bond angle depends upon the groups attached. But it does not deviate significantly from the optimal 109.5 degrees. If you recall our discussion of alcohols, an alcohol could hydrogen bond to another alcohol molecule. It was both an acceptor and a donor of hydrogen bonds. And ether, on the other hand, we draw an ether here, can only accept a hydrogen bond. So ethers can only accept a hydrogen bond. As a result, when you look at the trends in boiling point, ethanol has a much higher boiling point than dimethyl ether. If you look, the boiling point of dimethyl ether is almost as low as the boiling point of propane. Now, the ether is slightly higher because it has dipole-dipole interactions. Because of this bent shape there's a dipole towards the oxygen. So therefore, ethers have slightly higher boiling points relative to an alkane with a similar number of carbons. As you increase the R group on an ether, you can increase the boiling point. And this is due to London dispersion forces. So if you were to look here, we have dimethyl ether, The boiling point is negative 25 degrees C. When we move up to an ethyl substituent, diethyl ether, the boiling point is now 35 degrees C. And if we make these propyl groups, the boiling point is 91 degrees C. So you can see as you increase the R group, you increase the London dispersion and increase the boiling point. Ethers are typically used as solvents. Because they are fairly unreactive. Okay? But they are somewhat polar due to the oxygen. So some common solvents are diethyl ether, tetrahydrofuran or tetrahydrofuran, or THF, and 1,4-dioxane. Okay, another part of their appeal is the fact that they're volatile. They evaporate easily. I will say that these solvents are toxic. Okay. The THF and dioxane can accumulate in the environment and are reproductively toxic. In the past, diethyl ether was used as an anesthetic. It often had undesirable side effects, and when people would come out of anesthesia, they'd have nausea and vomiting. Now halogenated ethers are used. One of the newer anesthetics is called desflurane. And while it is understood how a signal is transmitted across a neurotransmitter, it is not clear on how these ethers affect the nervous system.